Well, chemistry deals a lot with chemical reactions, and we use chemical equations to represent chemical reactions as a shorthand, a concise method instead of writing long sentences. So here's an example of a chemical reaction. We've talked about reactants and products a little bit. So we have an arrow here, and the arrow is indicating that a change is occurring. And so these are the reactants. So here it's CH4 and O2. Those are reacting together. And after the reaction, we have CO2 and H2O. So the original substances are gone and new substances have been formed. These are the products. In parentheses, after each formula here is a letter, and that letter is indicating what state, what physical state is that substance in. Not all chemical equations have state symbols, but many of them do, and we need to know what they are. So here they are. They're not too tough to remember. G tells us it's a gas. L tells us it's a liquid. S tells us it's a solid. So this is pretty straightforward. AQ stands for aqueous, and aqueous means it's dissolved in water. So aqueous is a little bit like the Spanish word for water, agua, or if you think about an aqueduct, or an aqua lung, or aqua aerobics, or any of those things they talk about. Aqua refers to water. So aqueous, AQ, means dissolved in water. So if we look at this chemical equation that we've got here, here are the chemical formulas for the substances involved, and here are models representing those so that we can get a better picture of what's going on. So here's methane. It's got 4 white hydrogen balls and 1 black carbon ball. Here's oxygen. It's a diatomic element. It's one of those 7. So it's 2 atoms of oxygen holding hands, walking together. And then it makes carbon dioxide and water. Now, if you had these 2 little models, could you pull these pieces apart and make those 2 models out of them?
Yes.
Well, there's not enough oxygen. There's not enough red balls, is there? Over here, there's only 2, and if you put 2 here with the carbon, you don't have 1 over here to make this one. And then you also have leftover hydrogens. The white balls are left over. So what that means is that our description here is not quite right. Because the law of conservation of matter says that we can't create or destroy matter in a chemical reaction. So if we start with 4 hydrogen atoms, we have to end up with 4 hydrogen atoms. They can't just disappear. And if we start with 2 oxygens, we can't end up with 3 oxygens. It's not possible. So we need to fix the equation. The other problem is the hydrogens, as I mentioned. So 4 hydrogen atoms on this side. We can see that in the formula. And over here, there's 2 hydrogen atoms. And so what happened to those 2 hydrogen atoms? And they did not turn into the missing oxygen atom. That can't happen in a chemical reaction. So we need to balance the equation. The equation is giving us the correct formulas for each of the reactants and the products, but it's not giving us the relationship of how many is it taking. We can't have this reaction occur with just 1 methane molecule and 1 oxygen molecule. It can't happen. So to balance it, we can't change the subscripts on the chemical formulas because that would be changing what the substances are. But we can say there's 2 oxygen molecules by putting a 2 in front of this. So the symbol for the oxygen, the formula is still O2. But this coefficient is what we call it. The coefficient tells me I have 2 of those molecules. So now we've drawn 2 oxygen molecules. Now we see that we've got 4 total oxygen atoms, and we can put 2 into this one, and then over here We've got 2 oxygen atoms, and now we can make use of the other 2 hydrogen atoms, so we also need to put a 2 here. Yes?
So coefficients never represent bonds, right? Whereas adding a subscript would.
Yeah, coefficients do not represent bonds or anything like that. They just say how many of this molecule do you have. The molecule identity stays the same. It's like if you had,
2 Costco packages.
yeah, 2 Costco packages, or say 2 bicycles, right? And you needed 3, well, if you had 1 bicycle and you needed 3 tires, you can't just say, well, all of a sudden my bicycle has 3 wheels. Well, it's not a bicycle anymore, it's a tricycle. And you can't do that, right? So if you needed 3 wheels, you could have 2 bicycles, then you'd have 4 wheels, but you'd have to come up with a use for the 4th wheel. Okay? So it is very important to conceptually understand what this chemical equation represents. And that's why we've got the models here. I want you to be able to envision taking this model like it was Lego bricks or something, pulling these pieces off, pulling these parts off, and then putting them back together. We now have exactly the right number of each black, red, and white balls from this collection here to make these 3 new things. Do you see that? That's what's happening in a chemical reaction. Atoms are being rearranged. They don't become destroyed, they don't get lost, they can't be created, they're just partnering up with other atoms in a different way. Okay? The chemical equation is how we have come up with representing what is actually happening.